Imagine you have a particle of some kind. Imagine it's moving. Maybe it's accelerating or decelerating. Maybe it's being acted upon by a force. You would like to know where it is at any given time. You want something that looks like this, where x of t represents position as a function of time. This way, you can plug in whatever time you want, 2 seconds, 10 years, and out pops the position of the particle. This function or equation is commonly referred to as an equation of motion, or an EOM, as I'll refer to it from now on. Finding the equation of motion for a system has basically been the defining problem of physics ever since physics began. And the types of equations of motion that we have developed in the last even century have changed massively, and they tell you a lot about how we physicists view the world. My name is Sarah, I'm a physics student from Ireland, and today I'm going to be walking you through the main attempts at equations of motion in quantum mechanics. And in doing, basically walk you through a 4-year undergrad in a half an hour, so let's see how that goes. For all this to make sense, I'm going to assume that you have a little bit of background calculus knowledge. More specifically, I need you to know what a differential equation is. Don't worry too much about how they're solved, I just need you to know what they are. If this is your first brush with quantum mechanics, this might look a little bit scary, but don't worry. Learning how to interpret quantum mechanics and how to solve the equations that I show you today is going to come with a lot of practice and a lot of floundering, if I'm being completely honest, but that's okay, that's part of the process. If you go ahead and you take a physics class, what they're likely going to do is go into a lot of detail in deriving and teaching you how to solve and apply the equations that I show you today. And that's all well and good. That is not what I want to do here. What I want to do is just chronologically give you a map of the EOMs that you will have in your toolkit as a physicist. To use an analogy, where one physics class will show you in depth the features of a specific tree, I want to give you a map of the forest so that when you're in that physics class and you're getting totally bogged down by the tree, you at least know where in the forest you are. This video is about quantum mechanics, but I'm not going to start with quantum mechanics, oddly enough. I'm going to start with the ancient Greeks. Aristotle was said to be the first physicist, and he himself devised the first, I guess it could be called the first ever equation of motion. Aristotle's view can be summarized as force is proportional to velocity. Now, this is not something we still use today, but it was a start. Those who have ever had a glimpse of physics in their lives will recognize the lion by its claw. Isaac Newton very famously devised 3 laws of physics, and today I'd like to draw your attention to the second one, which states that force is directly proportional to the rate of change of momentum. Momentum is essentially a measure of how difficult something is to stop once it's moving. So imagine if you have a rock rolling down a hill. If the rock is heavier or more massive, it's going to be harder to stop. And if it's moving faster, it's also going to be harder to stop. So you can rewrite momentum as mass times velocity. So you can rewrite Newton's second law as force is equal to the change in mass times the change in velocity. Now, in most scenarios, mass ends up being a constant. So you can rewrite Newton's second law as force is equal to mass times the rate of change of velocity. But of course, the rate of change of velocity is acceleration. So force equals mass times acceleration. And a lot of the time, this is how you'll see Newton's second law written. Now, the mathsy folks will immediately recognize this as a differential equation. Depending on what scenario we're in, we can switch out force for for example, gravity or Hooke's law or whatever it might be, and we can write this in terms of position and a time derivative of position. Sometimes this is easy to solve, sometimes it's a bit harder to solve, but crucially, that's what we're working with. So Newton's laws are really good in most day-to-day scenarios. There are a few other techniques like Euler-Lagrange equations, things like that, but that's not what I'm going to talk about today. What I'm going to talk about today is what happens if you need to get subatomic. The thing about subatomic particles is that it doesn't really work if you think of them in the way that we've been thinking of classical particles up until now. So up until this point, you probably thought of a particle as like a thing, like a billiard ball or a rock, and it's got a definite position and a definite mass, and like, you know, it's here, it's right here, and it's moving around like that. And that doesn't hold up when you get into quantum. When you're dealing with quantum mechanics, we're not quite dealing with particles, we're dealing with what we call wave packets. A wave packet is going to look something like this. It's going to have a frequency, it's going to have this kind of spread, it's going to have a wave number, all that good stuff. So you can see here that it doesn't really make sense to give a precise location for the particle, because the wave function is spread out. As time goes on, the wave packet might move, or it might change shape, or any number of things. Rather than looking for a classical trajectory as we did in the Newtonian case, it would be better if we could model some kind of sinusoidal function that we call a wave function. So as long as we keep this whole wave function situation in mind, we can actually take a very similar approach to the one that we take in classical mechanics. We just have to be mindful of the fact that at the end, we won't get a position as a function of time. We will get this kind of sinusoidal function that will evolve over time. And that we call a wave function. The first ever attempt at defining an equivalent of Newton's second law, but for wave packets, comes in the form of the Schrodinger equation. Now, even though the Schrodinger equation was developed over 100 years ago, it is still considered the quantum physicist's bread and butter. Out in the wild, you might see it written in a lot of different forms, but fundamentally, they're all saying the same thing. Just to reiterate, I won't be deriving anything here. I just want to give you a feel for what the Schrodinger equation can do. Looking at the right-hand side, the term inside the brackets represents the total energy of the system, kinetic plus potential. We have a fancy name for this quantity because we use it all the time. It's called the Hamiltonian. On the left, we have the time derivative of the wave function. So we're looking at how it evolves over time. We can see that this I bar time derivative bit is equivalent to the Hamiltonian. As a matter of fact, I bar time derivative is actually the quantum mechanical way of saying energy. So what this equation says overall is that the wave function evolves over time according to its total energy. Okay, fantastic. So now we have the Schrodinger equation. The Schrodinger equation is all well and good, except there are certain properties it doesn't take into account. Most notably, it's not taking into account spin. Lots of people get very confused when trying to understand spin, but the simplest way to think about spin, for the purposes of this video at least, is to realize that particles that have spin react differently to magnetic fields than particles without spin. Those of you who are familiar with electromagnetism will remember that a charged particle, such as an electron, will generate a magnetic field when it moves. Particles with spin, when they're put into some kind of a magnetic field, will deflect as if they have some kind of inherent angular momentum That's where the name spin comes from. So, we need to amend the Hamiltonian in the Schrodinger equation to reflect this reaction. The left-hand side can stay the same. The only thing that's going to change is the Hamiltonian operator. I've written the Pauli equation here in terms of one spatial dimension in order to keep the notation as simple as possible for pedagogical clarity. It's worth keeping in mind that spin is an inherently three-dimensional quantity since it causes rotation in a field. Again, deriving this in detail is outside the scope of this video, but we can compare this to the Schrodinger equation and see our Hamiltonian operator has been given a little bump because of this spin reaction. Something I do absolutely want to make clear is that the output of the Schrodinger equation is no longer a scalar wave function. In the case of the Schrodinger equation, we were expecting a wave function that at every instance of space and time, there was one number. That number would correspond to the probability of finding the particle there upon measurement. In the Pauli equation, this is a bit different. We're expecting two numbers at every instance of space and time, and these two numbers represent the probability of finding the particle in spin up and the probability of finding the particle in spin down. So that's two numbers. We call these two numbers together a spinner. So rather than a scalar, we now have a spinner wave function. And this is the crucial difference between the Schrodinger wave function and the Pauli wave function. So from now on, we're dealing with a spinner wave function. Okay, so let's actually back to the Schrodinger equation for just 1 minute. The Schrodinger equation, as we said, it takes into account quantum particles very well. So electrons are described by it until you get spin involved, but we have the Pauli equation for that. But what if you have a particle that's moving at relativistic speeds, like a photon, for example? The Schrodinger equation actually fares quite poorly in those instances, and that's because the Schrodinger equation isn't accounting for any relativistic effects whatsoever. So these two guys called Klein and Gordon got together and they said, what if we try and incorporate at least special relativity into the Schrodinger equation? Remember how I said that the left-hand side of the Schrodinger equation represented energy? Well, in special relativity, energy is not just made up of kinetic plus potential, there's also mass. Any system that has mass has extra energy. So you've all heard of E is equal to mc squared. That refers to the amount of energy that the rest mass of a system has. So the rest mass is the amount of mass at rest, very literally. So in the case of the Klein-Gordon equation, the energy is going to be kinetic plus potential plus rest mass. Now, if we assume a free particle, the potential is zero, and that's a fair assumption in this case. So what we're going to have for our total energy is kinetic plus rest mass. So here I've written down the relativistic energy-momentum relation. I won't derive it thoroughly here, but it's essentially saying that the kinetic energy squared plus the rest mass energy squared is the square of the total energy of the system. As I said, we're going to assume a free particle, so there's no potential term. Bear in mind, what name did we have for our total energy? Bingo bango, that's our Hamiltonian. So let's pop that into our relativistic momentum energy relation in place of the Hamiltonian in the Schrodinger equation. We're also going to switch out momentum for the quantum form of momentum. What I've written down here is effectively the Klein-Gordon equation. Typically, you'll see it tidied up a little bit, and with the IH bar cancelled out on either side, with all the terms gathered together, just like this. And so you might say, yay, we're done. Slight hiccup. So if you remember what I said about the wave function being the probability of finding the particle in that position at that particular time, well, if the particle exists, then if you add up all of the probabilities across space and time, they should end up being 1. Well, that's what we call the Born rule, and it's a pretty good sanity check for whether or not our equations make sense. So what you can do is you can calculate something called the probability density. So essentially what we're saying is that if the particle exists, the probability of finding it somewhere is equal to 1. Now, once again, this video is not the place where we're going to be deriving this in detail. You can easily look up where all of these equations are derived. Even Wikipedia has them. But the point is, if you actually do this for the Klein-Gordon equation, you will disturbingly find that sometimes the probability density is negative. How do you have a negative probability for something? There's like a minus chance that you find the particle in a particular location, which is a bit mind-boggling. The other thing that you can do with the Schrodinger equation and the Pauli equation and the Klein-Gordon equation that I haven't really talked about until now is that you can solve for the energy of the system. So what you find is that you have these discrete values of allowed energy that you can have. So if you've ever heard of an atom having orbitals, that's actually a direct consequence of this. So you're going to have specific allowed energy states where you could find a particle. The problem with the Klein-Gordon equation is that sometimes you can have negative energies. So what you find is that you will solve for the energy and you'll get energy is equal to the square root of something. And if you know how square roots work, there is a positive square root and a negative square root of everything. So for example, 2 squared is 4, but also minus 2 squared is 4. So it doesn't really make sense to have a negative energy. Like, what would that even mean? What would that represent physically? So when people noticed this about the Klein-Gordon equation, even Klein and Gordon themselves saw this and realized, oh, maybe this isn't going to work. Maybe we got something wrong. I don't know. And it was kind of discarded for a while until this other guy, Paul Dirac, comes along and he reasons that, well, neither Klein-Gordon nor Pauli are taking into account the full picture. Klein-Gordon is only taking into account special relativity. Pauli is only taking into account spin. So what if you could have a version of the Schrodinger equation that takes into account both special relativity and spin at the same time? So if you remember from way back when, the relationship between energy and momentum in special relativity is squared. So it's E squared proportional to P squared. Dirac had the insight that if he could somehow develop a linear relationship between energy and momentum, then that whole square root situation might go away and maybe, hopefully, solve the issues that we have with negative probability density and negative energies. Let me get back to you on how successful that was. So the genius insight here, and it kind of comes as a little bit of a coincidence, because when Dirac wasn't thinking about a relativistic spin half Schrodinger equation, he was also thinking about matrix mechanics as a completely separate project. And so he had that at the forefront of his mind, and he realized that if he wrote the energy momentum relation like this, it would be fulfilled if alpha and beta were 4x4 matrices. Now, this isn't immediately obvious to me, but if you actually go through and you work it out, it does work. For the curious souls out there, what you want to look for is something called Clifford algebra. So now, if you take that linear relationship between energy and momentum and you substitute that into the Schrodinger equation in the exact same way that we did in the Klein-Gordon equation, you end up with this. And that is the Dirac equation. Now, you might see it written in a few different forms, but fundamentally it is saying the same thing. Now, you might be saying, Sarah, This was supposed to account for both special relativity and spin. You've only put in special relativity. Where are you going to account for spin? And this is the delicious bit. You don't need to account for spin manually, because spin just falls out naturally itself. Because we have introduced 4x4 matrices, the result coming out of the Dirac equation, so each point of the wave function winds up being a 4-dimensional spinner, so sort of like a vector. And the result of that is that naturally implies spin, because the extra 2 components are the 2 degrees of freedom of spin, spin up or spin down. You didn't even need to do anything, you got the spin for free. So now, you might say that's all well and good, but we remember our hubris going into the Klein-Gordon equation. We should check that everything makes sense before we go and declare ourselves the next Einstein. So let's go and first check that the probability density is always positive, and it is. No negative densities in the Dirac equation, we're all good to go. Now we check the energies, and we find that sometimes we still get that negative energy, we still have that square root, and that's pretty unfortunate, you know? Does that mean we have to discard the equation? No, says Dirac. Dirac has an explanation. Dirac came out of all this and was like, actually, what if the negative energy is actually a feature, not a bug? And everyone was like, Dirac, hun, I'm going to need you to elaborate on what you mean by that, because that, what does that even mean? So, basically, Dirac's idea is that all of those negative energy states that are seemingly allowed by the Dirac equation were actually filled by an infinite number of electrons. And this infinite number of electrons, just electrons all the way down, is called the Dirac sea. And in the event that there was a hole in the Dirac sea, well, this would be called an antiparticle, or a positron in the case of an electron, is what it's now known as. And if you're finding this explanation a little bit strange, you're in very good company, because every single one of Paul Dirac's contemporaries came forward after hearing this and was like, Paul, hun, this is the most boogaloo rationalization for a weird math result we have ever seen. You can't just invent a whole new type of matter because it makes your maths a little bit easier. That's not how any of this works. Sometimes we try things and sometimes they don't work, okay? It was a valiant attempt. You did a really good job, but it's just... Hey, Sarah? What? They found antimatter. What do you mean they found antimatter? Yeah. It was literally only a couple of years after Dirac found the Dirac equation. There were these guys who were doing an entirely unrelated experiment in a cloud chamber, and they accidentally detected a positron, as in like an anti-electron. Yeah, I know. How do you even do that? And that is how Paul Dirac, the absolute mad lad, ended up getting a Nobel Prize. Okay, so we've got as far as Dirac. We're pretty good. We have incorporated wave functions, spin, and special relativity. We're doing fantastic. Now, I am going to level with you. There has been a lot of work done since the Dirac equation was developed, as you'd imagine, and the concept of the Dirac sea is now considered a little bit outdated. We have replaced it with something called quantum field theory. If you've heard of quantum field theory at all, you will have heard of it because of Richard Feynman, who is super duper famous, even outside of physics circles. I have made the executive decision that today is not the day to be getting into QFT. This video is long enough. I'm also conscious that a lot of the people watching this might be their first ever brush with quantum mechanics, and if it has been, thank you for sticking around. This has probably been information overload for you. There is one small little thing that I want to bring up because it kind of is a little bit personal for me. The Majorana equation is very, very similar to the Dirac equation. As a matter of fact, it's basically identical, except there was this guy called Ettore Majorana. I apologize to the entire nation of Italy for how I'm pronouncing his name. And he realized that there's nothing in the Dirac equation that says that a particle can't be its own antiparticle. Fascinating concept. Now, we've never actually managed to detect a Majorana fermion. So a Majorana fermion is a particle that is its own antiparticle. And the reason I'm bringing it up is because it's something that I am actively working on. Here's the twist in the video. Big life update. I am about to start my research masters. I finished my undergrad. If you know me at all from anywhere before this video, you will know me from TikTok, where I accidentally went viral for talking about Majorana fermions. And the reason I was talking about it is because I was getting ready for starting my postgrad, which I'm going to be starting very soon. I'm just dotting the T's and dotting the T's. I meant dotting the I's and crossing the T's. But yeah, big, exciting life update. And of course, I will bring you all along with me. So watch this space.